Okay, hi everyone. We will try to continue into third video of this video series about mClock algorithm. Okay, in the previous video we already talked about how this algorithm works in detail, and then in this third video we will try to discuss about the specific issues, and also we will try to take a look at the experimental result. Okay, for the specific issue, we'll try to discuss the burst handling and then different parameters. For example, here is IO size, request type, request locations, and also followed by reservation settings. And then the first is how we can handle the burst request. Okay, this is related to the idle VM, and we will try to issue credits for this idle VM. Okay, for handling this burst. Okay, for normal, we will use this formula, right? This formula, and then for the idle VM, there is no request, so that there is no increment cap here. And then the first term will be much smaller than the current time, so that's why the maximum will output this current time here, this current time. This is the process before the tag assignment. Okay, so after this it's followed by tag assignment. This is just a note for you. Okay, and then for this burst handling, we will try to give it a credits by this credit value, these parameters. We will make the tag smaller a little bit, because we know that from previous algorithm, from the previous video, this algorithm will always choose a request with the tag value is the minimum one. Okay, to guarantee the reservations, the proportion, and also the limit specifications. Okay, by having this smaller value of the tag here, we put the higher priority of this VM. Okay, and then it can be specified by these parameters, and you can just use any number you want for each VM by setting these parameters. Okay, this is for the first specific issue, which is burst handling. We go to the next specific issue, which is how we can handle different IO size. We know that larger IO size requests take longer to complete, so we need to treat differently between the normal, small, and also the large IO. Okay, and then for the latency formula, we can just use this formula to calculate the latency, and then we try to convert from latency 1 to latency 2 to make a different treatment, right? So by using this formula, and this formula actually like a simple formula, just like proportional formula, which is latency 2 equals to latency 1, and this is the formula of latency 2, and this is the formula of latency 1. Okay, in this case we use n equal to 1, and also we divide tm. Okay, so that this term become 1, tm divided by tm1, and then this term becomes this one, tm times p peak here. Okay, this is how we can convert and handle the different IO size in mClock algorithm. And then we go next to the other specific issue, which is different request type. The request type can be read and also can be write. And this mClock algorithm treat read and write requests identically. So they will not do, for example, reordering, because reordering of them can lead inconsistency. Okay, so this algorithm just simply treat by using FCFS, first come first serve, or FIFO, first in first out, as IO scheduling within VM. Okay, take a note here, within VM, because we have queue here. This is the queue within VM. This is queue in the main algorithm that we discussed in the previous video. Okay, so in this VM1, for example, the first is comes from this read2 here. This is the second, and this is the third. So this is the queue. We will put this element into this global queue here. This is for VM 2. This is the first request, second request, the third request. This is also queue, FIFO. And then we put this element into this queue. And then for this queue, we will use this mClock algorithm to decide which requests will be processed by the system. Okay, again, by using FCFS without differentiating the treatment between the read and also write request IO. Okay, next we will try to discuss about how this mClock handle different request locations. Okay, we know that, for example, if we use a magnetic disk, okay, and accessing the data means that we access block by block. Okay, for example, if the block locations are different here, we need seek time, which is relatively long time compared to transfer time and other component time. And then this mClock algorithm will try to improve the performance by waiting little time but processing in a batch. For example, it will wait several requests. For example, we have like request 1, request 2, request 3. And for example, if this request 1, 2, and 3 come from this block, we can just process this all requests in the same time in a batch, instead of processing one by one and taking this block again and again and again. It takes longer time. So here again, we like wait a small time to get a bigger benefit by avoiding this seek time here. Okay, and also taking this block again and again. So this is how this mClock handle different request locations by using this batch approach here. Okay, and then next we will try to discuss how this algorithm recommend to specify the reservation of value, which is the lower bound of the VM. Okay, we can just use this formula here. IOPS equals to outstanding IO divided by latency here. For example, if an application requires 25 milliseconds average latency and typically keeps 8 outstanding IO, for example, how many IOPS does it need? We can just use this formula. So we have 8 here divided by this number. We have this 320 IOPS for the reservation. Okay, for example, this is for VM1. And for other VM, you can just calculate by using this formula, depend this latency requirement and also this number requirement. Okay, and then I think this is the last specific issue we will discuss. In this case, we will try to extend the normal mClock into distributed mClock. Okay, so we have this host, for example, in Taiwan, and the other host in Hong Kong, and it use same resource, a storage server. I mean, okay, how this mClock can be used in this distributed system here? Okay, we can just add one component, which is aggregate service here. Okay, we will try to aggregate in this variable row here, row, and also delta here. Okay, how we can use them? We can go to the next slide. Okay, so row here correspond to the served or finished or completed IO request in the reservation here, or we call it constraint based phase of VM1 or VMI, sorry. And then for the delta I here, it corresponds to the all IO complete requests for the tag L limit and also proportion. And this value is from the previous request, between the previous request to the current request. Okay, so for example, VM1, this value is for example 2, and then VM2, the value for example 1. Okay, so in this case we will have 2 and also we will have 1 for this delta I here. Okay, and then for the next we will give the higher priority for this VM2 here, because the VM2 only has one request completed. Okay, but again, this is also depends on the proportional share value. This is just for the gap interval. This is how normal mClock algorithm can be extended in a distributed system by recording this variable in this whoops, go back in this aggregate service here. Okay, that's all for the specific issues. And then next we will try to take a look about the experimental result of this algorithm. And this paper tried to compare with the existing method, which is SFQ. And in SFQ we cannot apply the reservation or minimum, and also limit for the maximum upper bound. Okay. Meanwhile, for by using mClock here, we can apply a limit, for example here 700, and also we can specify in the reservations, for example in VM4 here. And then the result, we can see the VM2 cannot be over this limit value. Okay, and then for the VM4 here, it can also be lower than the reservations, the minimum or the lower bound. Okay, so we can see that this mClock can successfully satisfy this reservation value, the limit value, and of course also the proportional value. Meanwhile, this SFQ, we cannot do this minimum and also maximum specifications of the resource allocations. Okay, that's all for the experiments, and we come to the last one, which is the conclusions. We can conclude that mClock successfully enforced reservations, proportions, and also limit over fluctuating I/O resource. Okay, and we can also conclude that dmClock, which is the extension of the normal mClock in distributed system, is also successfully implemented in cluster storage system architecture. Okay, for the current state, mClock is adopted in VMware vSphere version 5.5, and then dmClock is adopted in open source software in CEPH. Okay, and then this is the references that we use for this video series. I already mentioned in the first video, I think. So if you want to take a look at the detail of the paper, you can just read this paper here. Okay, and that's all. Thank you very much for watching. I hope this video series can be useful for you, and see you in the next video. Bye bye.